All right, example 4 of composition of function. In this case, we had a function absolute value of x minus 2 and the rational function for x plus 2 over 2x squared minus 5x minus 3. Well, we have to find the domain of these two functions first. Well, the first one, the domain is going to be all real numbers because absolute value of x minus 2 is just the graph of the absolute value function that is shifted to the right by 2 units, and it's going to look something like this. So all of the x value will be eventually taken on as the graph go all the way to negative infinity and positive infinity. Now, what about the domain of this rational function? Every time I see rational function, what I like to do is I like to factor it out. So factoring out the numerator, I'm going to have 2 times 2x plus 1. For the denominator, it is going to be factored out to be 2x right here and x right there. That's for the first term. And to get this last term, negative 3, and to also get the second coefficient, negative 5, I'm going to try plus 1 here and minus 3 over here. So let's see, 2x foiled to the x is 2x squared. 2x foiled to negative 3 is going to be negative 6x. 1 foiled to x is 1x. Negative 6x plus 1x is negative 5x. 1 foiled to negative 3 is negative 3. So this is the factor form of this. Now the domain of the rational function can be found by taking the denominator, the factor denominator, 2x plus 1 times x minus 3 and set it not equal to 0. Using the zero product property, set each of these binomial factor not equal to 0. So we are going to have 2x plus 1 not equal to 0, and then x minus 3 not equal to 0. So this is going to give us, let's see, 2x not equal to negative 1 over 2. Divide both sides by 2, we get x. Oops, this is negative 1, my bad. This is negative 1, and then divide both sides by 2. That's when we are going to get x cannot be equal to negative 1 over 2. And this is x cannot be equals to positive 3. So we got 2 restrictions for this function. And of course, if we factor it out, take a look. In the numerator, you have the terms 2 multiplying the term 2x plus 1. And in the denominator, you have the term 2x plus 1 multiplying the term x minus 3. So the 2x plus 1, which gives us the point of discontinuity at x not being negative 1/2, is actually removable discontinuity. And it is a removable discontinuity because we have a common term 2x plus 1 that can get canceled out. So that is why it's a removable discontinuity. So when you graph this function, you will see that the graph, it seems like it actually passes through the point x equal to negative 1/2. But if you click on your graph, you would see that there's an open circle at the point x being negative 1/2 on your graph. But anyway, what about the composition f of g of x? Well, f of g of x basically is the entire function g right here, replacing all of the x of the f function. So that's only that one. So that means we are going to have absolute value of 4x plus 2 all over 2x squared minus 5x minus 3, and then all of this minus 2. But hey, this can be factored out to be like this. So we are going to have 2 times 2x plus 1 all over 2x plus 1 times x minus 3, and then minus 2. Like that. Now what about the domain of this? Well, to find the domain of this result, we have to state all of the restriction of this result. Well, the restriction that we can see in this case is this little denominator, because if the denominator here is 0, then everything is going to be undefined. And that's going to make it impossible to do this composition of function. So we have to do the same thing as we did for the g function. Take each of these binomial factor and set it not equal to 0. solving for x individually, in each case, we are going to have x cannot be equal to -1/2, and x cannot be equal to 3. That is the restriction of the result. Now, what about the restriction of the inside function? Well, that happens to be the same restriction as the ones that we just come up with. So that means the domain of this composition of function is all real numbers. Except x cannot be equal to -1/2 and 3. And if you were to write this in interval notation, you would see that on a number line, let's say this is -1/2 and this is 3. We exclude that, so we put the open circle. Well, from left to right, we want to go from -infinity up to -1/2, but not touching 1/2. So parentheses, -1/2, -infinity, comma, -1/2. Then close, and then parentheses again, because we're excluding it. Now, the part in between, still excluding -1/2 and +3, we are going to have union, parentheses, -1/2, comma, 3, and then close, and then parentheses again. Well, last one. We are going to go from excluding 3 and all the way to +infinity. So union again. 3, comma, +infinity. And that's the interval notation for this one. And of course, the union can be interpreted as the word or. So you say the interval from -infinity to -1/2 or this on that. All right. And I'm not gonna evaluate this as x equals to -2 because I'm too lazy. I'm just gonna go ahead and do g of f of x. Well, g of f of x can be found by taking this entire function f, which is absolute value of x minus 2, and you plug it in to this entire function g. You can plug it in here or in here, but I like to plug it in here because it's already factored out, so that's a little easier to see. So that means I'm going to have 2 times 2 times absolute value of x minus 2, and then plus 1, and then all over 2 times absolute value of x minus 2, and then plus 1, and then absolute times absolute value of x minus 2, and then minus 3. Now with the f function plugged in, I got this little thing. Well, take this little rational function, or take the denominator and set it not equal to 0. So I got the domain. It's going to be 2 times absolute value of x minus 2 plus 1, and then times absolute value of x minus 2 minus 3 not equal to 0. And so using the zero product property, take this, set it not equal to 0. So I got 2 times absolute value of x minus 2 plus 1 not equal to 0, and then comma, x minus 2 minus 3 not equal to 0. What about the first part? Well, the first part, this right here, this part is actually just the graph of the absolute value function that is translated to the right by 2 units, translated up by 1 unit, and being vertically stretched by a factor of 2. So it's probably going to look something like this. So this part is always going to be positive no matter what. If you take a look at this function, because all of the function value is going to be at least 1 or higher positive values like that. So that's why this part of the domain is always going to be positive. So we're good on that. But this part is something that we got to be careful of. So solving for absolute value of x minus 2, we get absolute value of x minus 2 not equal to positive 3. Well, remember back in algebra 1, absolute value of something equal to something, we are going to have two cases. Case 1, x minus 2 cannot be equal to negative 3, or x minus 2 cannot be equal to 3. Solving for x individually, we are going to have x cannot be equal to negative 1, or x cannot be equal to 5. So the restriction of the result is x cannot be equal to negative 1 and x cannot be equal to 5. What about the restriction of the inside function, absolute value x minus 2? Well, the domain of the inside function is all real numbers already, so we got no restriction. So the only restriction for g of f of x is just these two x values right here. So the domain of this is going to be all real numbers except x cannot be equal to negative 1 and 5. What about on interval notation? Well, I'm going to use another paper for that. Well, for interval notation, it's going to be helpful to draw a number line. So let's say I got negative 1 here and 5 right here, and we are excluding those two values. So put the open circle right there. Always read the number line from left to right. So we only go from negative infinity up to negative 1, but not touching negative 1. So this part is that interval. Union, or the word or, this middle part, from excluding negative 1 up to 5, but not including 5. So negative 1 comma 5. And then union again, this part, from excluding 5 all the way to positive infinity. That is the domain of g of f of x.